So the recording has begun. Just confirming that the recording is still on. So share my screen again. So this is not the title of the course, it's just the title of my slides. But I will send you the full title of the course. Now I will try to cover these 4 topics for today. A lot of it will be informal, not in the typical way it's covered in a mathematics class. We'll focus on what the understanding the concepts and an intuitive approach so that you can quickly be able to use the content in applications. So in this class, you will not see any applications, but have no fear, the applications will come at some point. So we'll start with the following setup. We talk about this Euclidean 2-space. This is something you're familiar with, the set of all ordered pairs of real numbers, usually denoted by this R2, this symbol. So we call these kind of things, these ordered pairs, vectors, and we shall denote them instead of using this horizontal or row notation, we shall be denoting them as columns. So our vectors will be denoted as columns. So this is an example of a vector. We shall define the general case of vectors in a short while, but this is an example of a vector. And then the good thing about this R2 is you can actually draw, you can represent these as points in the Cartesian plane, also called the XY plane. So this is familiar to you. You've already worked with this. You just think of these points, these what we call the points in R2 as our vectors, and they will take this form. So once you have a set like this, you need to put some structure on it to be able to call it a vector space. So to put some structure on it, we need to define some operations. We define vector addition. So here we're adding 2 vectors. We pick 2 examples, 1, 2, and 3, 4. These are two vectors in R2, and we want to add them. So that's how we shall add them. We simply add components that are in the same position. So 1 is added to 3 to get 4. 2 is added to 4 to get 6. So that is how you add them. One more example down here, how you add them. So this is one operation that you impose on the structure, on the set R2, which we call vector addition. So it's not just integers that can be in the vectors, they can also have other types of numbers in the vectors. Any real number can be in the vector. I think it's just convenient to write integers, but any other real number can be there. So the second option you have is to multiply the vectors by a real number. So for instance, we have this vector 4, 9, we multiply it by 2, and that is as simple as multiplying every element by 2. And our result is 8, 18. Here's the second one where we multiply the vector 15, 24 by a half. That means we multiply every entry in here by a half, and the final answer is 7.5, 12 as our vector. So this second operation is what we call the scalar multiplication. We're able to add vectors, and then we're able to multiply them by scalar. In this, what scalar stands for is just a number. Scalar is just a big word for number. So now the set R2 combined with those 2 operations is actually a vector space over R. There are more properties that are involved, but those are the two most important properties for us now. So we shall focus on those two properties. There are about 8 other properties for some set under some operations to be a vector space, but we shall focus on just those two for now. The others are rather intuitive. They will make sense as we use them. So we have a special vector in which both entries are 0, and that is called the 0 vector. And we denote it by this bold 0. And if you add 0 to any vector, it doesn't change. So v plus 0 is the same as 0 plus v, and it doesn't change. It's equal to v for any vector that you pick from R2. There's also another special vector, which is called the negative of v, and it's simply denoted by minus v. So if you add v to its negative, you get back the 0 vector. Right? Is that making sense so far? So this is still quite informal. It's not the standard way to introduce vectors, but we are starting with things that are familiar, and hopefully they will build up to make sense. So now we can extend this to a larger space. This is R3. So we still have vectors in this column notation with 3 entries now instead of 2. So 3 real numbers. That forms the vector space R3. So this will be the second one we consider. Again, the beauty about this is you can still draw in 3 dimensions. You can actually draw in a 3-dimensional space with the X, Y, and Z axis. You can plot the points in space. So on the same set, you can define vector addition. Here we give an example of vector addition where we pick 2 vectors, 1, 3, 7, and 7, 5, 10. When we add them, we just add components in the same position. We have 1 plus 7 to give you 8, 3 plus 5 to give you 8, and 7 plus 10 to give you 17. You can also do scalar multiplication. Here we choose this vector, 1.5, 0.29 multiplied by 2. And this is the answer. You simply multiply every element by the scalar. So again, this set R3, together with these 2 operations of vector addition and scalar multiplication, they form a vector space over the real numbers. So the reason we say a vector space over the real numbers is because the scalars that we use are real numbers. It's also possible to define a vector space over other fields like the complex numbers, but we'll focus on real vector spaces. Real meaning the scalars are real numbers. So you can extend it further to any finite dimension so that we have Rn. This time you will have tuples. So you have n numbers in some order, and each of the numbers are supposed to be real numbers. You can add them the same way you add, if you have 2 vectors, you can add them the same way you were adding the numbers, but now we have made it a little more general. You add components in the same position of the 2 vectors all the way to the end. That gives you the sum. You can also multiply by a scalar alpha. That means you multiply every component of the vector x by the scalar alpha. Now again, this will form a vector space over the real numbers under these 2 operations. So once you go beyond 3, once n goes beyond 3, you no longer have access to the ability to draw. So now you have to focus more on the algebraic techniques of working with vectors. And most of the applications in real life will have n way larger than 3. So it makes sense to study these things because they actually appear in life. It makes sense to generalize to other finite dimensions, higher finite dimensions, because most of the time you do work in those, if in applications, you'll be working in those higher dimensions. But the same ideas that you, especially for this vector space, what you do in the lower dimensions, it easily translates to the higher dimensions. So by understanding what happens in the lower dimensions as examples, you can still follow it in the higher dimensions. We will not focus too much on these higher dimensions until when we need to, but I thought we should just introduce it at this point. So are we okay up to that point? Kuna maswali? So in general, like I told you, there are many other properties that are satisfied by a vector space over the real numbers. In this case, we are considering this specific vector space Rn. There are many other types of vector spaces that don't look like Rn at all, but we shall not look at them. We'll focus on Rn because most of our work will involve data, and the data will be built from vectors in Rn. So I think for now, we can focus. There's some benefit on working with complex numbers as well, but maybe towards the end, we can introduce that. For now, we'll focus on real vector spaces. So these are all the properties. The first two are the ones we have considered. That is, no, not the first two. This first one for vector addition. If you add any two vectors, you will get a vector in the same set. The other one is this one here for scalar multiplication. I think I should label this as scalar multiplication. Those are the two main properties we have worked on. So the others try to say more about addition. Then the ones down here try to connect the scalar multiplication and the addition. So most of these other properties are quite natural from what you have been doing. So we focus on just these two. This vector addition, you need to understand what that is, and the multiplication by a scalar. That is this property here. So now we look at, once you have some vectors and scalars, it's possible to construct new vectors. And that process can be done using linear combinations. We're about to define those. So this can be done in any dimension, but we shall consider vectors in R2 and R3 for now, as we shall show in the next slide. So here we are, linear combination. So we'll start with a set of vectors. We pick some vectors in R3. So I think someone is trying to join. Let me see if I can admit them, then I get back to the class. I will figure out how to make someone an admin. I've never done that on this platform, so I will not try to do that now. But next time, I think I should make someone else an admin so that they can admit anyone who joins that. Yes? You need to keep your mics off if you are able to, so that we don't get interrupted. Okay, so now we are talking about linear combinations. we pick some vectors in R3 and we try to get different combinations. So we get a multiple of any of the vectors added to a multiple of another vector. And this kind of operation is called a linear combination of the vectors u and v. So we multiply u by 2 and add it to 3 multiplied by v. And when we work them out, we get the final answer as 5, 8, 21. So we can say that this vector 5, 8, 21 is a linear combination of u and v, because we've been able to find some numbers, 2 and 3, which satisfy this. So you're not limited to 2 vectors. You can get a linear combination of 3 vectors, and you can have negative factors. They don't have the multiples don't have to be just positive. You can have negatives as well. So this gives you another linear combination of these 3 vectors, u, v, and w. So you can always construct another vector from a set that you have through this process. So linear combinations. Is someone trying to speak? Do you have a question? They've gone quiet. So if you switch the scalars, because this you are not limited to just the scalars that you have put here, you can put any numbers, any real numbers as your coefficients here. Then you keep getting new vectors that are linear combinations of the given vectors. So in general, if you work in Rn and you have a set of R vectors, you can have a corresponding set of R scalars, and a linear combination is simply the sum of multiples of the vectors. Multiply each vector by a scalar, and then add them up. This gives you a linear combination. So all these things we are defining, you need to have them at your fingertips, because at some point we shall refer to them rather casually, and you need to understand what they are, all these terms, linear combinations and other terms that we shall introduce as we go along. So this is a general form for a linear combination of vectors in Rn. So based on that, we can also introduce the concept of linear dependence. 2 vectors will be linear dependent if it's possible to express one as a multiple of the other. So that's the case for 2 vectors. If you have 2 vectors, it's simple. They'll be linearly dependent if one can be written as a multiple of the other. So an example of this is here. We have 2 vectors. U is 4, 6, and V is 2, 3. And we observe that 4, 6 can be written as 2 times this vector 2, 3. So since we can see that U is actually a multiple of V, then we can conclude that the 2 vectors U and V are linearly dependent. So they depend on each other. The dependent is quite deliberate, the wording. It's also possible to reverse this. You can write V as a multiple of U, because V can be written as a half U. That will still work. So for the case of 2 vectors, it's quite easy. You just check that one is a multiple of the other, and if that happens, we declare that they're linearly dependent. If you have more than 2 vectors, then how do you tell if they're linearly dependent? This happens if one of the vectors can be written or expressed as a linear combination of the remaining vectors in the set. We'll see an example shortly. So here is an example of 3 vectors in R3. You observe that any one of the vectors, W, V, or U, can be written as a linear combination of the other 2. So for example, you can observe that W is equal to 2U plus V. It's important that you double check this. It's usually possible to make mistakes, but we can just double check. If you multiply U by 2, you will have 2 here. And If you add to 1, you get 3. I think it makes sense. What about the last one? Multiply 2, you get 6. 6 plus 7 is 13. Yeah. So I think the rest also makes sense. If they don't, you should be. That's why I insist that you must have a pen and paper. That way you can double check some of the work that is on the slide. So every vector here can be written as a linear combination of the remaining 2. And that means that these vectors are linearly dependent. So anytime you have a set of 3 or more vectors, they will be linearly dependent if any one of them can be written as a linear combination of the remaining vectors. So there's a more general, more formal way of defining linear dependence. And this is how it goes. If it means we define this for a general vector space Rn. So if you have R vectors from Rn, so each of these is a vector in Rn, we'll say that they're linearly dependent if you can find R scalars, that is alpha 1 up to alpha R, and not all of them should be 0. At least some of them should be non-zero, such that if you set up this linear combination, you get 0. So this also simply means you can express any one of them as a linear combination of the others. So for instance, if I want to express U1 as a linear combination of the others, I will simply push this U1 to the left, or rather push everything else to the left. If they move to the left, they all have negative coefficients. And then I divide everything by alpha 1. Then I'll be able to write U1 as a linear combination of the remaining vectors. You can do the same for any other vector in this expression. So it still fits in with our definition where any vector in here can be expressed as a linear combination of the remaining vectors. Okay, I think someone was trying to join again. Is it that people have a bad connection, internet? I think they're now admitted. Let's see if we can go back to the slides. So this was defining linear dependence in general. The next concept we look at is linear independence. So we can define, first of all, we illustrate it using some vectors, then we shall define the general case. So a single vector on its own is considered to be linearly independent. When the case of two vectors are linearly independent, if it's not possible to write one as a multiple of the other. So if this is not possible, then the two are not linearly independent. So for instance, if you consider this example, you have these two vectors, 1, 2, and 1, 3. So it's not possible to find a number to multiply by V to get the vector U. It's just not possible. If you try to solve that, you will see that there's no solution to that. And also just by inspection, you can see clearly there's no number you can multiply by 1 to get 1 and then multiply it by 3 to get 2. It simply won't work, right? There's no number that can satisfy that condition. Or vice versa, a number which you multiply by 1 to get 1 and the same number multiplied by 2 to get 3. There's no solution. So these two are linearly independent because it's not possible to write any of them as a multiple of the other. So that works for when you have two vectors. That is two vectors, whether they're in R2 or R3 or Rn, this statement still holds. So the next one is we have two vectors again in R3 now. Again, if you look at this carefully, it's simply not possible to find a number which, when multiplied by V, you will get U. There's no scalar which can satisfy that condition. So again, these are just two vectors. It's easy. So we could try to check if our statement is true. So in general, if you have three or more vectors, they'll be linearly independent if none of the vectors can be expressed as a linear combination of the others. So this is a general case. Here's an example with these two vectors, U1 and U2 and U3. We claim that they are linearly independent. So if you pick any one of the vectors and try to find two other numbers, say A and B, such that U1 is equal to AU2 plus BU3, there will be no solution to this. No such numbers exist, right? Yeah. And since now it's not possible to write any one of them as a linear combination of the remaining two, then we conclude that this set of vectors are linearly independent. They do not depend on each other at all. So an attempt to find those, we go back a step. An attempt to actually find these values of A and B is here. So we try to equate this vector to a linear combination of the other two vectors, 0, 1, 0 and 0, 0, 1. So of course, after you multiply this out and add, this is what you get at the end. But you can see it gives us some contradictions. It suggests that 1 is equal to 0 and that 3 is equal to 1, which can't work. There are no numbers A and B which will satisfy this, which will make this possible. So the other way the casual way to do that is to look at the first slot. The first slot is 0 here, and this for that first vector on the right-hand side, and it's 0 again for the second vector on the right-hand side. So there's no way you can multiply these zeros by any number to add them and get 1. It just won't work. So that is just a casual way of looking at it. So these three vectors are therefore linearly independent. There are better ways of checking that vectors are linearly independent. We'll encounter them as we go along. We need a few more tools to be able to do that. So the formal definition of linear independence is down here. It says if you have R vectors, these vectors will be linear independent if whenever this linear combination equals 0, the only way that can happen is if all the coefficients are 0. So if the vectors are linear independent, this equation can only hold if all the coefficients are 0. So again, maybe the other thing I should add is that we want this to be non-zero vectors. None of these should be the 0 vector. Are we together so far? Nani amepotea? So for those looking for some hard maths, don't worry, it will come. This is just a welcoming party. We will encounter some good mathematics later. So the other thing we're going to look at is basis and dimension. So let's consider these two vectors, U and V. The first one, U, has the components 1 and 0, and the second one is 0 and 1. So these are two vectors in R2. And if I pick a vector, say 3, 5, I can write it as a linear combination of U and V as follows. W will be equal to 3U plus 5V. I think this is self-explanatory. And in general, if I pick any vector in R2, it is possible for me to write it as a linear combination of these two. So any vector AB is simply A multiplied by this first vector plus B multiplied by the second vector. So that means if I wish to construct any vector in R2, I only need these two vectors, U and V. I keep changing the coefficients and I can construct any vector in R2. So these two are enough for me to build the whole of R2. Is that making sense? Mnaogopa kuongea?
Unaweza rudia? Can you please repeat that on the basis and dimension?
So look at this carefully. You have, and ideally you should have a pen and paper so that you write them down. So look carefully. You have two vectors, U and V. Right? The first one has a component 1, 0. Second one has a component 0, 1. Then we take some other vector 3, 5, which we call W in R2 as well. And we see that we can write W as a 3 multiplied by U plus 5 multiplied by V. You can check that. If you multiply this by 3 and this one by 5, then you add them, you should get 3, 5. So those are the things you need to do by hand as we go through the slides. You need to verify those things. You will understand better if you do that. If you just stare at the screen, you will miss a lot. Maths is a writing subject. You can't learn by staring. So is that clear up to that point?
Yes, I have a question.
Yes.
In layman's language, Euclidean, what is Euclidean space like?
This is layman's language.
No, that's how you. I don't know how
this
to
is
put it.
We have not done.
Why are we using R2? Why are you using the R3? The R which is the simplest way to understand this space that we keep on talking about in numbers? Numbers have spaces.
What do you study in undergraduate?
I did statistics, but this course wasn't. Yeah, this one we dropped it. So.
Yeah. So if it's supposed to be harder than this. What I'm putting on the board is very elementary. You will just have to take this as a gospel truth. And then vectors are not entirely new. Some of this is high school work. So you should have a rough idea of what these are. The only thing that has changed is now we are talking of R2 instead of the Cartesian plane, drawing the vectors in the Cartesian plane. So think of these as just the points in the Cartesian plane, 1, 0 in the Cartesian plane and 0, 1 in the Cartesian plane. So this one cannot be simplified beyond this. If it's simplified beyond this, it will not make sense for this course.
The number changes depending on the number of values in that particular vector. For instance, if W had maybe 4 points or 3, let's say 3 points, so our space would have been R3.
That's correct.
Okay.
This one is defined here. If try to pay attention to the definitions. Here it is, the n-dimensional Euclidean space. So Rn talks of n numbers. For you, this should be obvious. If you have done statistics, you must have covered things that look like this, or at least close to this. The notation should not be confusing for you.
Okay. Thank you.
So this is a definition. We have n entries, and if you have n entries, we talk of Rn. So the other thing is also you must find time to look at this letter. A lot of these things, you cannot understand them with one sweep. You must find time for them. There's no magic pill you can swallow to understand this. There's only one solution. You sit down and compute them. Later on, you don't finish class and then put them aside. If you do that, they will not make sense later. Ideas are what you are doing in high school for vectors. Up to now, we have not done anything beyond the concepts. Maybe just working with the three-dimensional vector space. Other than that, it's the two-dimensional space is the same vectors you're working with in high school. I think this one needs more examples. I was assuming this should be relatively basic to everyone, but it appears to be not the case. But you cannot avoid this. You just have to go through the pain. There's no shortcut. So I can share some books, but the books will have more detail than this. Any book you pick on linear algebra will not be this simple. It will have a lot more detail than this. But I will still share some books which you can look at. So we've checked. No, I think we had seen this. We've also given the definition of linear independence. There are other ways of checking for linear independence, but again, like I said, we need some new tools to be able to do that, which we haven't learned. For now, we are trying to do that using simple examples. So we'll continue with this basis and dimension. So let's pick two vectors in R2. What we have shown is that at the end of it all, we have shown that if you pick any other vector in R2, it's possible to write that vector as a linear combination of these two vectors, U and V, right? So another observation you can make is that these two vectors, U and V, are linearly independent. In other words, it's not possible to write any of them as a multiple of the other. So U and V are linearly independent. And then also observe that any other vector in R2 can be written as a linear combination of these two vectors. We have used this one as an example. 3, 5 can be written as 3 multiplied by U plus 5 multiplied by V. Okay. So pay attention. Don't try to overthink this. We just have two vectors in R2. We have shown that if you pick any other vector in R2, you can write it as a linear combination of those two vectors. The other thing you need to pick up from here is that these two vectors are linearly independent. That you can quickly check. It's not too hard. So we will need that information. Keep it, hold on to it. So This is just repeating what I said. Any vector in R2 can be written as a linear combination of U and V. So because of that, since any vector in R2 can be written as a linear combination of these two, we say that those two vectors span R2. So this is also another term that you need to pick up. These two vectors, they will span R2. We also mentioned that U and V are linearly independent. So when you have this kind of situation where you have a set of vectors in R2 that are linearly independent, and they span the whole of R2. In other words, span means any other vector can be written as a linear combination of those vectors. Then such a set of vectors is called a basis. In this case, this one is called a standard basis, the one that consists of one of the vectors as 1, 0, and the other one as 0, 1. It's called a standard basis. So this is the simplest basis you can have. And for this one, it's very easy to construct linear combinations of vectors in R2, because if you have a vector AB, you simply multiply A by U and V by B and add them and you get the vector. So this one is the standard basis. Okay. So now it is not the only basis, but any other set of two vectors that are linearly independent in R2 will also be a basis for R2. A lot of these have a lot of mathematical proofs behind them, but I'm trying to give them to you as gospel truth. So take this as a fact, something that you can use. Any set of two linearly independent vectors in R2 will be a basis. So we'll define a basis shortly, what it means. So here's a list of definitions. The first one talks of a set of vectors in a given vector space. Is said to span the vector space if any vector in V can be written as a linear combination of the vectors in the set. Right? So back to my slide. We have said that these two vectors, U and V, they span R2 because any vector in R2 can be written as a linear combination of U and V. So that covers the spanning bit. Then the next definition we're looking at defines a basis of a vector space. So if you have a vector space, then a set of vectors in V will be a basis if first of all, the set is linearly independent and also spans V. So in our case, the vector space says that we have worked with will just be R2 or R3 for our examples. We'll work with higher dimensional ones later, but for now, we can stick to these two just to understand the concepts. So the other thing is that the number of vectors in a basis of a vector space is called the dimension of the vector space. So this number does not change. If you have a finite dimensional vector space, like in our case, R2 and R3, the number will never change. You can have different sets of vectors, but the number of vectors in a basis can never change. So if you find one basis, then it means any other basis will have the same number of vectors. We found one basis for R2. It had two vectors, and therefore any other basis for R2 will also have exactly two vectors and no more. So here is another pair of vectors in R2. The first one is 1, 0, and the second one is 1, 1. You have 1, 0 as a first vector and the second one as 1, 1. So again, here you'll have to take a leap of faith. Don't ask me how I got this. For now, accept this as the truth and nothing but the truth. Some of you probably know how to do this, but the reason I decided to drop it here is because some may not know, but it works. That's the important thing. Know that this expression works. So we have two vectors, u and v. You can verify that these two vectors are linearly independent because it's not possible to write v as a multiple of u, likely because of this 0 here. There's nothing you can multiply by 0 to get 1. So u and v are linearly independent because u cannot be written as a multiple of v, or vice versa. So now the next statement picks a vector, an arbitrary vector in R2. Then it can be shown that this vector can be expressed as this linear combination of u and v, right? So with a minus b as a coefficient for u and b as a coefficient for 1, 1. You can expand this just to confirm. So what is on the right-hand side, if you multiply this first component by a minus b and the second one by b, so you'll have a minus b plus b, you will get a. That confirms. The second one, multiply a minus b by 0, you will get 0. Then b by 1, you will get b. Then you add 0 plus b, you should get b. Okay, so this is a different set of vectors. Initially, remember we had 1, 0 and 0, 1. Now we have a new set of vectors, 1, 0 and 1, 1. So this new set of vectors is still possible to write any other vector in R2 as a linear combination of these two vectors, as shown here. So don't worry how this is obtained. Right now, take it as a gospel truth. We shall eventually learn how to solve systems of linear equations, and this will fall in place. So are we together up to that point? Yeah, for now, you have to take it as a gospel truth for now. You will, I'm avoiding the advanced things first. Any questions up to that point? So mathematically, this should make sense to you. As a mathematician, this should be easy for you to verify. You can just plug in the values and see that it works. That is what is important for now. So applying that formula, this formula that we have here, if you apply it to a given vector. So for instance, if we pick a vector like 5, 3, so your A is 5, your B is 3. If you apply the formula to 5, 3, you can see that it's possible to write 5, 3 as a linear combination of 1, 0 and 1, 1. So that is 2 times 1, 0 and 3 times 1, 1. We simply apply the formula. You can now double check if this actually works. Expand this and compare with the initial vector. You should see that they're equal. So we have a second example is here, which shows that 2, 7 can be written as minus 5 times u and 7 times v. So these are just examples of the application here. But what we have shown here is that we have two vectors in R2. The two vectors are linearly independent. We have confirmed that. None can be written as a multiple of the other. And we have also shown that the two vectors span R2. Span means any vector in R2 can be written as a linear combination of these two vectors. Okay. So have you seen what's going on up to that point? We have confirmed those two. The two vectors are linear independent and they span R2, and therefore they form a basis for R2. So this gives us another basis for R2, and you have infinitely many different bases for R2. So these are just two examples. There are many different pairs of linearly independent vectors that you can find in R2, and any pair of linearly independent vectors in R2 will form a basis for R2. So here is another pair of linearly independent vectors in R2. And again, you can check that if you pick any other vector in R2, it's possible to express it as a linear combination of these two vectors with these as the coefficients. This is a little more interesting with some numbers. A little more interesting coefficients. So again, this is not hard to solve. It's just a solution to a system of linear equations. We shall learn how to do that later. But for now, all we are showing is that you can get more than one basis for R2. In other words, you can get many different pairs of linearly independent vectors, and any such pair will span R2. That can be proved in general, but again, if we do that, I think now everyone will run away from the class. If a statistics student is having trouble with it, if we do the actual proofs for this, I think I might be left alone in the class. So is this making sense so far? This now you should verify this by hand, multiply this out, and confirm that indeed if you multiply this out on the right-hand side and add them, you should get AB. That is how you do mathematics. There is no easy way out of it. You pick a pen and a paper and write them down.
Excuse me, sir.
Yes.
We have some people that are asking to be admitted into the class.
The Teams did not ring the bell for me on this side, or maybe I didn't hear. Yeah, there are about 4 people. Let's bring them back in. So next time, I think I'll make Kibet maybe I should also put off the video. Sometimes this affects people's connection. It's lighter without the video. There's still one person in the. I think it's fine. Let's go back to the lecture. So like I said, this one you must sit down and verify. Otherwise, you can't learn this by staring. And I can't make this equation any simpler than this. So your solution is to sit down, multiply these things out carefully, add them and confirm that they indeed are equal to the left-hand side. Later on, we shall see how you solve this and get them. Some of you already know, so I don't think this is strange to everyone, but for now, we don't need to know. We're just trying to show how a basis works. So applying that formula to this vector, you see this last formula, if you pick any vector in R2, you can express it as a linear combination of 2, 7 and 1, 5. So you just need to identify what is your A and what is your B, plug them into the right-hand side, and you solve your problem. So here, as an example, we pick 6, 9. We plug in the values, A as 6 and B as 9. And then we compute this, and we get that 6, 9 can be written as 7 multiplied by this first vector, 2, 7, minus 8 multiplied by this second vector. So again, take time, multiply this out, add them up, and confirm that indeed they will equal this left-hand side. So this remaining topic. Or we can give you time to try to double check these values. We take a maybe 10-minute break. You double check some of the things you have written, because some of those concepts you have written, you need them for, you need to carry them with you to the next section. So we can take a 10-minute break if that is fine. Otherwise, if you don't want the break, we can continue.
We want it.
Okay. So it's 7:53. We resume at around 8:03. Okay.
That's okay.
Okay.
It's fine.
Ah.
If you're speaking, you're on mute.
So I think you have and maybe gone over some of the things you've written. Is there anyone with questions on what we have done so far? So the other thing I noted, I've just checked the charts. There's someone who is asking about practical applications. Now, you will have to be patient. You have a whole semester. You have to learn the tools that you will use to apply. So first, you must understand the tools, then you can apply them. You cannot apply what you do not know. So, and if you want to know about applications, I think it's quite easy to know. Just go to ChatGPT, ask about the applications of linear algebra in data science. You go to YouTube, there are so many videos showing that. You'll get a more comprehensive answer. So make use of all other resources as well. We will get to applications, but for now, please put the applications aside, understand the tools. We will get to the applications where we use the tools. So I'm happier now if you forget about applications until we get to them. I want you to understand the tools. And if you go for a data science interview exam, you probably will do things that are harder than this. So you have to get used to this kind of thing. So hakuna maswali from the previous work. We can continue. So now we'll talk about coordinates. So we've seen that if you have in R2, you can get several different bases. Now each basis for R2 will work for any vector because you can write any vector as a linear combination of the vectors in a basis, right? So for example, here we have the same vector, but in 3 different bases, the same bases that we have used before. So 6, 9 can be written as 6 times 1, 0 plus 9 times 0, 1. So that's the first basis for the same vector. If you use a different basis, this basis 1, 0 and 1, 1, the coefficients change. For the same vector, the coefficients will change. If you use a different basis again, for the same vector, you can see these coefficients change. So these coefficients are what we call coordinates. When you change a basis, the coordinates also change. So the ones you're used to, the coordinates that you're used to are these ones where the coordinates of a vector are the same as the components of a vector. That is when you use the standard basis. So 6 and 9. So most of the time you express coordinates of the vector 6, 9 as just the same as the point 6, 9, because you're working with a standard basis. So if you change the basis, you get a new set of coordinates for the same vector. So anytime you change the basis, again, you get a new set of coordinates, but for the same vector, right? So basically, those are the things that we call coordinates, these coefficients. But now you have to say coordinates with respect to a given basis. So with respect to this first basis, 1, 0 and 0, 1, the coordinates of 6, 9 are just the same values, 6 and 9. If you change the basis to 1, 0 and 1, 1, the coordinates of 6, 9 will be -3 and 9. And this keeps going like that. If you change the basis to 2, 7 and 1, 5, the coordinates of 6, 9 will be 7 and -8. Okay. So with that, now we can define the basic idea behind coordinates. So if you, this can work in any other space, but I'm sticking to R2 for now to make things easier. So if you have a basis for R2, then any other vector we have seen earlier, if it's a basis, you can always write any other vector as a linear combination of the basis vectors, in this case, U and V. Now these numbers, these coefficients, are what we call the coordinates of the vector W with respect to this basis. The other thing I will mention that it's important to call it an ordered basis. Order, because if you switch the order of these vectors, then the coordinates also change. Instead of AB, now you'll have BA. Okay, so it's the order of the basis vectors is important. So once you fix an order, you stick to that order. So in this case, we will say that these values A and B are the coordinates of the vector W with respect to the basis U and V. We have seen examples here. The coordinates of 6, 9 with respect to standard basis is just 6, 9. The coordinates of 6, 9 with respect to this second basis will be minus 3, 9, and so on. Basic idea behind coordinates: when you change the basis, you get a new set of coordinates. Later on, you will see the basic ideas behind it. I mean, the purpose of that. So here, I think this is just repeating what we have done. Now we label these bases B1, B2, and B3, and then we pick the coordinates of 6, 9 with respect to these different bases. We already worked out these coordinates in the previous, in this slide. The coordinates are already here. So I'm just picking them from here and now putting them in this slide. Writing out just the coordinates of the vector. So the next one is just a remark that talks about the standard basis, and the standard basis is the same one we have worked with, and the coordinates of any vector will be the same as the entries of a vector. Is that making sense up to now?
Yes, it is.
Good. So now we move to R3. Earlier on, we already defined a basis. I think we also saw an example of a basis for R3. So here's a set of vectors which are linearly independent. There are ways to check that they're linearly independent. For now, you will just have to accept it again as a gospel truth. And be patient. We shall eventually see how you check that they're linearly independent. For now, some of you already know how to do that. So maybe I can, if you know how to determine, to compute the determinant of a matrix, you can put this into a matrix and compute the determinant. If the determinant is 0, then this set of vectors will be linearly dependent. If the determinant is non-zero, then they will be linearly independent. You can check that on your own later. So anyway, for now, let's agree these are linearly independent. And then we pick any other vector in R3, not R2. Since we are in R3, this should be R3. There's a typo here. I should go and correct it. So you can show that such a vector can be expressed as a linear combination of these 3 vectors. So this gives you the coordinates of this vector ABC with respect to this basis. So the coordinates will be A minus C, A minus B minus C, and C. Okay, so you can apply this to an actual vector. I don't know whether I have. Yes, there. So you can apply it to this vector 2, 7, 3. So this take 2 as your A, 7 as your B, and 3 as your C. then you're able to write this same vector as a linear combination of these three. So it's important that you try to double check this yourselves. Don't just take this at face value, write this down and try to compute this and confirm that indeed this vector equals to the one on the right-hand side. So now once you work this out, we've been able to write this vector 273 as a linear combination of these vectors in the basis. So these coefficients are what I will call the coordinates of the vector 273 with respect to this basis. The basis is here, this basis B. And this is the formula we use for computing the coordinates for any vector in R3. So again, now just accept this for those who don't know. Otherwise, we will overload with too much information at the expense of the concepts. So we also saw earlier that for R3 or R2, R3 in particular, we have found a basis that has 3 elements. And we also mentioned earlier that a basis for a vector space will always have the same number. Any basis will have the same number of elements. So if you just find one that works and it has 3 elements, then any other that works will also have 3 elements. So you could try this with the standard basis for R3. You would see for the standard basis, the coordinates will still remain the same, 2, 7, and 3. The standard basis would be the one that has 1, 0, 0 as your first vector. The second vector in the basis will be 0, 1, 0, and the last vector will be 0, 0, 1. Then you are left with these are just the coordinates will be the same as the entries in the vector. But if the vector is not the standard basis, then the coordinates of the vector are different from the entries in the vector, as you can see in this case. So this again just emphasizes what I said earlier. You have to stick to the order. If you change the order, the coordinates change. Therefore, you have to fix an order for the basis and stick to it. I think we are almost done now. So the first remark simply repeats what I'd said earlier. Working with the standard basis, the coordinates will simply be the same as the entries in the vector. I think I've skipped this one. Now, if you're working in Rn, then the dimension will be n for Rn in general. So any set of n linearly independent vectors in Rn will form a basis. Okay, keep that in mind. These things will come up later in a little more detail. For now, just take them as they are. So since the number of vectors in a basis for Rn is actually n, then the dimension of Rn turns out to be n. The simplest example of a basis is the standard basis for Rn. We've seen the standard basis for R2. And then if you have the basis, you can always, since it's a basis, any vector in Rn can be written as linear combination of the same basis. And then these coefficients become the coordinate of the vector with respect to that basis. So now, once you have fixed the basis, the coordinates are unique. In other words, it's not possible for a vector U to have 2 different sets of coordinates for the same basis, right? So for instance, if you consider this basis that we worked with here, the coordinates of U with respect to that basis are -1, -8, and 3. So there's no other set of coordinates that will work. This is the only one. It's unique. So this repeats what we were saying, standard basis. So then later on, we shall see that you can construct other bases which make it very easy to calculate the coordinates. And in particular, the kind of bases I'm referring to are the orthonormal bases. We shall learn about this later. These orthonormal bases are very useful in your applications. But once you understand them, then you can apply them. So another thing about one last statement, maybe you can make about a basis. A basis is sort of maximal in some sense. If you add, it's a maximal independent set. In the following sense, if you add an additional vector to the basis, then your new set of vectors ceases to be linearly independent. It now becomes linearly dependent. And also, if you exclude just one vector from the basis, then the new set no longer spans the vector space. It will still retain the linear independence, but it will no longer span the space, the vector space. I will stop there. Maybe when we start next time, I can expand on these ones so that you don't have an overload. In any case, those are all the slides are prepared now. I have a set of accompanying notes which I'm preparing that gives a little more detail on what appears in the slides, which I will share. I need to clean it up and add a little more meat. And based on the interaction, I think I really need to add a lot more meat on the notes for it to make sense to everyone. So questions? It can mean one thing, either it was too easy.
I have a question.
Yes.
I might have missed the explanation, but why do vectors in dimensions have to be linearly independent?
They don't have to be.
Or they don't have to be? Sorry, I didn't hear you.
Yeah, I think you've missed a lot of the class. They do not have to be linearly independent, but you can have a set that is linearly independent. You need to go through this very slowly. The vectors do not have to be linearly independent at all. There's the conditions for linear independence that were set. We started out with the simple case. If you have two vectors, they are linearly independent. So there's a keyword here which says if. One cannot be expressed as a multiple of the other. So if tells you they must satisfy some condition before they are linearly independent. Okay, so you need to understand exactly what condition must be satisfied for the vectors to be linearly independent. Now we gave an example here of two vectors in R2, which are linearly independent, and this should be easy to check that there's no way you can find a number to multiply by this to get this vector. So I picked simple examples where you can just check by inspection. It's just not possible to find a number which, when multiplied by these two numbers, will give you these two numbers. So U cannot be written as a multiple of V and vice versa. So this set is now linearly independent. The second set here also of these two vectors in 3 dimensions are also linearly. So for the case of two vectors, it's fairly easy. You can check that. For the case of 3 vectors, you can check that they are linearly independent. Again, there's a word here that says if. If means they must satisfy a condition for that to happen. It's not always true. Does that answer your question?
Yes.
Yeah. So I'll just share these slides anyway. Then you can look at them. I think the recording is also somewhere. I'll try to download it and share later.
Excuse me.
Yes.
There's a remark that you said that if we add an extra vector to the basis, the new set is linearly independent, and if we do not do so,
Independent.
still remains linearly independent, but does not span over the vector space. Do you have maybe an example? Maybe we can try with a number or so that we understand how the linearity independence still remains, even if the span space is omitted.
So for avoiding proofs, if you want to understand that, we have to go into theorems again. It will just make things more complicated. But let's see if I can find some space on one of the slides and write on one of the slides. So I'll give an example here. I'll just give the case of 2 dimensions. You can still see my screen, eh?
Yes.
So we have these 2 vectors, say 1, 0. Let's start to the standard basis. That's the simplest case. So 1, 0 and 0, 1. You can see what I'm writing. So this is a
Yes.
This is a set of 2 vectors, which forms the standard basis for R2. So now we know very well that this B, we have confirmed that it actually spans R2, right? What does it mean when we say spans R2? So a lot of this only makes sense if you sit down and absorb the concepts. If you don't absorb the concepts, everything becomes confusing. And like I said, you cannot absorb them in one go. This is a master's in data science. So there's a reason it's called a master's. You're becoming a master. You have to do something a little different from what anyone else would do. So you can't do it in one go. You must go back and sit down and read these things. Okay. So now there is a basis for R2. So we have said 2 things. Now, if I add an extra vector, so for instance, I pick any other vector, like 2, 3, and add it to this set, then what will I have? I will have 1, 0. Then I'll have 0, 1. So let's add another vector to the set. So previously it was a basis, and then a basis, is made up of, it's a linearly independent set. But now if I add 2, 3, then something has changed, because now I'm able to write 2, 3 as a linear combination of these other vectors. So now it has lost that property of being linearly independent, because now if I add a 3rd vector, I can still write I can now write one of the vectors as a linear combination of the others. If this happens, then the set is no longer linearly independent. Right?
Yes.
So by just,
so
and then
just
it also follows the logic. We know that this set spans R2. So any other vector in R2 can be written as a linear combination of this spanning set. So if I add that vector to this set, then I'm guaranteed that that new vector I add can be written as a linear combination of the vectors in the basis. So then it loses that property of independence, because the vectors now become dependent on each other. So that covers the case where you add one more vector. If you drop a vector, is this clear?
Yes, it's clear now.
Yeah. So now if you drop a vector, in this case, there are only two, so maybe it's not a good example, but let's just use it anyway. If you drop one vector, you are left with only, say, 1, 0. By definition, we say that a single vector is considered to be linearly independent, right? So it doesn't lose the property of independence, but it loses another property. Now, I cannot, so now this single vector cannot span, does not span, doesn't span. I need to get a pen for the screen, then I'll write better. This is, I'm using the mouse. It's making my handwriting look like class 2. There. So 1, 0 does not span R2. What do we mean by it does not span? Because there are some vectors. So for instance, if I pick a vector like 0, 2, I cannot write it as a multiple of 1, 0. So I've lost that property. There's no way I can write this as a multiple of 1, 0. There's no number, such number, which can satisfy this. So it's still linearly independent, but it does not span R2. So just if you drop one vector, you lose the spanning property. You still retain the linear independence. If you add one more vector, you still retain the spanning property, but you lose the linear independence.
So ideally, the vector that you add will affect, the type of vector that you add is the one that will affect.
It doesn't matter which vector you add. It's not the type. Any vector that you add from R2. The reason for that is we already said that a base, if you have a basis, then any other vector in the set can be written as a linear combination of these two.
Okay.
So you have to sit down and read everything line by line and carefully. There's no shortcuts to this, please. You really must find time for it. You make sure before you move to the next page, you understand the definitions on the previous page, because as you move ahead, you need everything you have done before. Like what you have done now, you must know it for the next class. Don't cheat yourself that this is hard. This is not hard at all. What we are doing here is very diluted. If you pick a proper linear algebra book for data science, you will see what I mean. This is highly diluted.
I have a question, and sorry to take you back.
Yes. No problem.
So does it essentially mean that R2 is like rows? So R2 means 2 rows, R3 means 3 rows in a vector.
Like this. Okay. Now, when I write something like this, does it make sense? That makes sense to you?
Yes.
What does it mean?
1, 2, 1 dimensional.
This is not one dimensional, it's 2-dimensional. It's a 2-dimensional vector because it has 2 components in it. So anything that is of this form, in general, if you have anything that is of this form, you have the first entry as X, second one as Y. In our case, we are considering only cases where X and Y are real numbers. they can belong to another field, but as you can see, we're already having trouble with these real numbers. So maybe we should just stick to those, not do any other field. So if these two values, X and Y, are both real numbers, then this is a vector in the R2, a vector in the space R2. That's all. So if it has three values, so if you have X, Y, and Z, now you change from R2 to, now this is a vector in, just a number of components have increased, keeps going like that. It can go to as many as 5. So for instance, if I have X1, X2, I'll just use dots to indicate that. If it goes all the way up to X5, now I have a vector in R5. So R5 is a set that consists of any vector that looks like this. And it can go to any value that you like. 5 is just where I have stopped, but it can go to as many as 10 million. And this actually does happen in real life, because when you're working with data, you can have very large dimensions. An example is websites are treated as a network. Some are connected, some are not, and each website can be treated as an element in a vector. And there are over 64, well now I think way more. There are billions of websites, so that is a vector that contains more than several billions of values. So each website, of course, can be assigned a number which ranks it. So what will appear now in the vector are the ranks of the various ranks of the websites. So I don't know if that answers your question.
Yeah, it does.
So read this carefully. Read both the English and the mathematics. The English will answer a lot of your questions. So words as simple as if and so on, they make they make a lot of difference if you account for them. So sit down carefully and read this. After you read, maybe you will have more questions, or probably some of what is not making sense will make sense. Mmemaliza maswali ama bado kuna zingine?
Okay, maybe the last one. I'm just requesting if you can also share the course outline to guide our reading.
The course will look very different from this because it has a lot of advanced things. So you will have to, I can share the outline if you like, but if I follow that, half of you will be out of the class by now. Or 3/4. Either out of the class or you'll be hunting me down to shoot me
That sounds scary.
In the toast. Yes, it's data science. This is data science, Bona. You have come to do data science, not a programming. It's not a programming course. It's I don't know if there's anyone here who has tried to do one of those data science interview tests. They will tell you what you do is more advanced than what I'm doing now. Pardon? Nevin is saying something? Or
No,
it's a bit broke.
no.
Okay. So please, next time you come to class, make sure your name is written in full. Like there's someone here who is YBM. I don't know who YBM is. No, we don't know whether that one is in one of us or not. So next time, make sure your name appears not initials or only one name. If you can't do that, I will have to remove you from the class until you're able to put a full name. So for today, you have been told, you're warned now. But next time, when you join, make sure you have your names, their full names. So there's Philip is asking if we can get the notes. Yes, I will share the notes. There's one or two errors I need to fix, then I share. I will also share a book so that you can actually see that what I'm teaching is a little watered down. Some of you may think that what I'm teaching is advanced, but it's not. It's not at all advanced. This is the basic stuff. So yes, classes will be at 8:30. I mean, not 8:30, 18:30. I'm usually not back home by 5:30, so we can't have the class at 5:30. So we can be starting at 18:30 every week. If I'm able to start earlier, I can inform the class representative earlier. At least one day before. Okay, so I think I need to stop recording.